Motion of a heavy symmetric top or gyroscope is very interesting, and there are many types of it, such as sleeping top, regular precession, motion with cusps, and looping motion. In this video, we will consider sleeping top and the fall of the top. If one spins a heavy symmetric top, one may observe this type of motion. If top spins fast enough, it may come to the upright position, which is known as the sleeping top. Rise of the top will be considered in another video. To analyze sleeping top, we need reference frame. We will use this stationary reference frame. Here the z prime axis points upward and the symmetry axis of the top coincides with the z prime axis. We know that top spins around the symmetry axis with some angular velocity, say psi dot. Since there is an angular velocity, there will be a corresponding angular momentum. And we know that there is a gravitational interaction which results in a force which is equal to m times gravitational acceleration. To understand this type of motion, we need a relation between torque and angular momentum. For translational motion, we know that the motion is described by Newton's second law, which states that force is equal to mass times acceleration. And we know that the acceleration is the time derivative of the velocity. And for classical mechanics, mass is constant. Then Newton's second law can be written in this form. Force is equal to time derivative of the translational momentum. And from this relation, one can say that force describes how translational momentum changes with respect to time. There's an analogous relation to this one, which states that torque is equal to time derivative of the angular momentum. And from this relation, one can say that torque describes how angular momentum changes with respect to time. And torque can be found by taking cross product of r with f. In the sleeping top case, the gravitational force points directly to downward and it passes through the fixed point, which means that r is equal to 0. Then torque will be equal to 0. And from torque-angular momentum relation, one can say that angular momentum is constant. This is valid for the ideal cases. However, in real cases, there will be always dissipative effects and the angular momentum will decay. Let us try to understand the motion of the top by using this video. As it is seen, top is in the sleeping top motion. Even one touches it continues its motion. This is valid for fast tops, which is known as the strong top. And as time passes, its angular momentum decays and it becomes weak top and it touches to the ground and it fell down. Now we will try to understand the fall of the top. In the video, we have seen that as time passes, the symmetry axis of the top deviates from the z prime axis. To understand the fall of the top, we need another reference frame, which is body reference frame, and it is fixed to the top. It is z-axis anchored to the top symmetry axis, and the angle theta shows the deviation of the symmetry axis of the top from z prime axis. As the top deviates from the z prime axis, the top develops another angular velocity, which is shown in here by phi dot, and it describes the rotation around z prime axis. In the sleeping top case, we have seen that due to the rotation around the symmetry axis, there is an angular momentum. In this case, that angular momentum will be shown by Lz. And there is another angular momentum since there is another rotational angular velocity, which will be shown by Lz prime. The calculations related to the full dynamics of this motion is a bit complicated. Then for simplicity, we will follow a different way. During the sleeping top stage, this Lz and Lz prime were overlapped, and as angular momentum decays, we have seen that the top deviates from the z prime axis. Since Lz and Lz prime were overlapped initially, we may consider that they are equal to each other. But the dynamics of the motion is more than this one. We know that there's gravitational force, and differently from the sleeping top motion, this force causes a torque, which can be shown in this way. Since we have obtained this torque from the cross product, this torque is perpendicular to both z and z prime axes, and naturally it is perpendicular to Lz and Lz prime, which means that it doesn't change their magnitude. Their magnitude changes due to the dissipative effects only. Firstly, let us consider the sleeping top stage of the motion. We have seen that during the sleeping top stage, top is stable and symmetry axis points directly to the upward position, which means that theta is equal to 0. When Lz and Lz prime are equal to each other, the form of the effective potential is in this form. One can consider effective potential as a function describing changes related with theta. As it is seen, the minimum of this effective potential is at theta equal to 0, and any deviation from the theta equal to 0 will result in the theta equal to 0 case due to the dissipative effects. And for the later stages of the motion, we have seen that top deviates from the theta equal to 0 position. When top becomes weak, the form of the effective potential when Lz and Lz prime are equal to each other changes in this way. In this case, the minimum of the effective potential occurs somewhere different than the theta equal to 0. And since theta is different from the 0 for the minimum of the effective potential, we have seen that there is a circle in this case, and symmetric top follows that circle, which is the result of the form of the effective potential. And for more later stages, the form of the effective potential changes further, and the minimum of the effective potential occurs at greater theta values. And as it is seen from this video, the radius of the circle becomes greater. And as top continues to its motion, dissipative effects reduces angular momentum, and it results with further changes in the form of the effective potential, and finally the top touches the ground and it fell down. While explaining the fall of the top, we have considered that magnitudes of angular momentum in the body z direction and stationary z prime direction are equal to each other. However, they can be different, and we will consider what happens if there is a small difference between the magnitudes of these two angular momenta. We will consider a heavy symmetric top that is used for an experiment in previous work and studied numerically in this work. You can find links for mentioned papers in the explanations of the video. We will choose initial values as theta 0 is equal to 0.001 radian and theta dot is equal to 0, phi dot is equal to 0, and psi dot is equal to 126 radian over seconds. This corresponds to a situation that a spinning top is set into motion with a small inclination. We will numerically solve this case by considering the dissipative constants given in this paper. One can calculate values of Lz and Lz prime as these. As it is seen, Lz and Lz prime are very close to each other, and they remain in that way for 48 seconds in the numerical solution, and after that Lz prime gradually becomes greater than Lz. Nevertheless, let us see the results of the numerical solution. These are the animated plots of the numerical solution. On the left, an animated three-dimensional plot of the symmetry axis motion is seen, and on the right, an animated plot of the effective potential is seen. The horizontal line shows E prime, which is a constant derived from energy, and the black dot shows the intersection of theta and E prime values at the shown time, which is visible at the upper right corner or at the down left corner. The nearly vertical line at the left shows the fall of the top at the beginning of the motion, which is explained in Goldstein classical mechanics. During this fall, the top develops precession angular velocity phi dot and continues its motion with that value. If there were no dissipation or dissipative effects were small enough, then the motion with cusps or its dissipative version could be observed. After developing precession angular velocity, the top rotates around the z prime axis, and as a result of the dissipative effects, angular momenta E prime and the form of the effective potential changes, and the inclination angle gradually increases. We should note that these values are very small and these changes can hardly be noticed by the naked eye. It can be understood from the left animation that precession angular velocity increases as time passes. The change in the form of the effective potential is more noticeable as time passes as a result of approaching becoming weak top, but these changes are still very small. Around t is equal to 43 seconds, the top becomes weak and the scales of the graphs are changed. On the left, we see a dot showing the position of the symmetry axis, and all previous changes did take place within that dot. The form of the effective potential is totally changed since the top is weak anymore. And after losing some more angular momentum and energy, the top makes a motion similar to the spiraling motion. Then it makes a dissipative version of motion for the slope top when angular momenta are equal. These motions will be explained in the follow-up videos. Most probably, around these times, the top's disk will touch the ground and it will fall down. However, the simulation continues to the nearly horizontal position. We have explained the motion of the spinning symmetric top, the sleeping top. It is the simplest motion. Then we have continued and gave an explanation of the fall of the top in simple terms, though the motion is pretty complicated. And we considered a numerical solution. One can find links related to scientific works in the explanations of this video. Nevertheless, this video is related to a small part of the motion of a heavy symmetric top. Even if we have explained all the different possible motions of a heavy symmetric top that we are planning to do in this video series, that is a small thing. In fact, whatever a scientist does, it is a small contribution to the science. Being small does not mean that it is unimportant. On the contrary, it is very important because science is constituted from these small things. In addition, in time, with the help of other scientists, that small thing can be transformed into a very important thing. Some people may consider that their work will be transformed into very important things. For me, the important thing is the contributing to the science, and I am not interested in whether my contribution is transformed into a very important thing or not, probably not. Being a part of the scientific community and a student of science is enough for me. Let us consider Galileo Galilei. He was trying to understand the fall of an object by using the motion on an inclined plane by using his pulse at the beginning and then later a pendulum in a basement. At that time, many people considered these things are unimportant. Even today, some students and even some professors may find that making experiments on an inclined plane in the freshman laboratory is an unimportant thing. But it is very important. because that experiment opened the way to the Newton's second law, which lies on the very foundations of nearly all scientific works in physics. All scientists study small things. Sometimes we may consider these as very big things, but they are not. The big thing is the science. Thanks for watching. Stay with the science.